For section 7.2, we'll be looking at the law of cosines, which is a set of formulas that allow us to solve for either a side length or an angle measure in an oblique triangle. That is, again, a triangle that has no right angles in it. So in general, we could have 3 acute angles for an acute triangle, or we could have 1 obtuse angle along with 2 acute angles. Now you may notice when looking at the formulas for the law of cosines, formula 1, 2, and 3 right here, that at the start they look exactly like the Pythagorean theorem, and then there's included an additional term which is subtracted from it. Okay. And in fact, that is correct. If in fact the angle measure in any one of these 3 formulas, if that angle measure happened to be 90 degrees, then we would have exactly the Pythagorean theorem. Recall that the cosine of 90 degrees is equal to 0. So so for instance, take a look at this triangle here. If it turned out that angle A was in fact a 90-degree angle, then this would have in fact been a right triangle. And that right triangle would have had a hypotenuse of length A. The side length A over here would be the hypotenuse if angle A was 90 degrees. Well, notice that the law of cosines formula then, by that construction, where angle A is 90 degrees, this term negative 2bc cosine A, that would all just equal 0, because cosine of 90 degrees is 0. And again, if angle A was 90 degrees, then the side length A would have been the hypotenuse. So this would have been the correct formula for the Pythagorean theorem. The same would have been true for the other 2 formulas. Right? Normally we write the Pythagorean theorem like this, right? Where c squared is equal to a squared plus b squared, because we're normally saying that side length C is the hypotenuse, and normally saying that the angle C is the 90-degree angle when we have one. Okay, so but we can see that the formula is true, or that the formula can be used regardless of which side lengths we want to solve for, or which angle measure we actually are interested in solving for as well. Notice that in the formula, whichever side length is isolated on the left-hand side of the equal sign, that is always going to be the side length that is opposite of the only angle that you find in the equation. All right? So this first equation here, the only angle measure that we see in this equation here is angle A. And angle A is opposite of side length A, which is the side length that is isolated on the left-hand side. The next equation down, side length B is the one that is isolated, and that is the side length that is opposite the angle B, which is the only angle that shows up in this equation. Right? And in the third one, same story. The side length C is the one that is isolated on the left-hand side, and that is the side length that is opposite the angle C, which is the only angle that shows up in the formula. Okay, so that is useful for remembering how to set up the formula in exactly this way. If you're going to use the law of cosines, start by writing a Pythagorean theorem. Okay, an a squared equals b squared plus c squared, for example, and then whichever side length is the one that you've chosen to isolate when you set up that Pythagorean theorem, make sure that the angle that is opposite that side length is the one that you end up taking the cosine of in the final term. Also to remember for the final term is it's going to be a subtraction. There's going to be the coefficient 2, and you're going to have a product of the 2 other sides. That is the other sides, the sides other than the one that was isolated, right? So for instance, in the second formula, if we have it solved for b squared, where b is the isolated side, then it is the product of the other 2 sides, a and c, that will show up in this remaining term. So in that way we can remember how to set up the law of cosines. Now, the other 3 ways that it is written over here is simply just, this is solving the formula for the cosine A, cosine B, or cosine C. So if you wanted to use these three forms, it would just be one step away from solving for the angle measure contained in the law of cosines. Of course, you would solve any one of these three equations over here by taking the arc cosine of both sides. Recall that using the inverse cosine is going to restrict the domain of the cosine function to quadrants 1 and 2. So it's possible to get solutions to these equations here that are either in quadrant 1 or quadrant 2. That is, we can get an acute angle, that would be an angle in quadrant 1, between 0 and 90 degrees, in other words, or an obtuse angle. That would be a quadrant 2 solution, which is between 90 and 180 degrees. Both are, generally speaking, possible solutions to triangles, because it is possible to construct a triangle with acute angles, and it's possible to have a triangle that has one obtuse angle as well. Okay, so there's two sets of formulas here, but primarily I stick with these right here. These three formulas right here, for me, make up the law of cosines. The ones to the right of this line are simply just manipulations of those formulas to isolate the cosine term. Okay, so I would stick with these three right here. Now, let's just pick any one of these and take another closer look at it. What is involved in the formulas? Okay, we have, for any one of these formulas, we notice there is a measure of a side length, a side length, a side length, a repeat of a couple of side lengths, and an angle, right? So in each one of these, we see that there are, that these formulas are built up using three sides and one angle. So that means that we would be able to use these formulas if we have three of these four components and wanted to solve for the fourth one. For instance, if we had the case side, 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 that is, if we already knew three side lengths of a given triangle, okay, then we can use law of cosines, okay, in order to find an angle. Okay, right? Because if we already had three sides, then we plug those three side lengths, A, B, and C, into this equation, and we would be left with solving for the angle. What else could we do? What if we had a side angle side? That is, if we had two of the sides and the one angle, right, then we can use the law of cosines in order to find the remaining side. All right. What's another possibility? Well, the other one is the ambiguous case, where we could have two sides and an angle in that order, okay, clockwise or counterclockwise, and then we can use the law of cosines again to find the missing side. But note that this is the ambiguous case. Okay, and the ambiguous case has 0, 1, or 2 possible solutions. We have to take that on a case-by-case basis. All right. We've looked at that before with the law of sines. Okay. Now, when comparing this to the law of sines, notice that these formulas are more complex. They're more complicated. First of all, they involve more operations than the law of sines. Right? We think that the law of sines has you take the sine of an angle and then you divide by a side length. Then you take the sine of another angle and divide by a side length. That's only 4 operations for the law of sines to be used. Take the sine of 2 angles and divide by 2 side lengths. That's 4 operations total. But within the law of cosines, anytime we use a law of cosines, let's look at the operations we need. We're going to have to square a side, square another side, and another side. That's 3 times we have to square things. That's already 3 operations. We're going to have to add. That's a 4th operation. We're going to have to subtract. That's a 5th operation. we're going to have to multiply a 2 times b times c. That's a product, okay? A product and a product. Then we're going to have to multiply again. Then we're going to have to take the cosine of an angle. In other words, we certainly have more than 4 operations going on in this formula. You're going to be hitting more keys on the calculator. Take a look at it that way. You'll hit more keys on the calculator to do the law of cosines than the keys you will have to hit when you do the law of sines. That's what I mean by operations. So the law of cosines, we would say, is more expensive. It's more computationally expensive than the law of sines. And for that reason, if we have a case that we could use the law of sines, we should use the law of sines instead of the law of cosines because it's less expensive to do the law of sines. And consider if we have the ambiguous case, right, the side-side angle. If we have side-side angle, recall that we could use the law of sines or the law of cosines. And if we have the choice between the two, I'm always going to choose the one that is less expensive to use. We might as well, right? Why choose a formula that is going to require us to do more work when there was already a formula that required less work? So I'm instead going to focus on using the law of cosines only if nothing else would work. That is, the law of cosines is the most expensive formula we have for solving triangles. Okay? And I'm only going to use the law of cosines if we are in a side-side-side case or a side-angle-side case. Because in either of those cases, the law of sines will not be available to us. Because as we discussed in the previous section, for either of these two cases here, we will not have an angle that is opposite a side that is already known or that is easy to find. So we're stuck. We have to use law of cosines in either of these cases. Once we find one more component, then we'll be able to choose to use something else, like a law of sines, for instance, to complete the solving of a triangle. Okay? So of our 6 cases that we've already looked at before, it still is the case that angle, angle, angle has an infinite amount of possible combinations of side lengths, but angle, angle, side, and angle, side, angle are each going to be cases where the law of sines is particularly available. And again, remember, it's not just memorizing the different cases here. I'm suggesting read the given information in the problem, draw yourself a good diagram, and label all the known information in the diagram. And then consider, if you can use the law of sines, you should be able to determine an angle measure and the side length opposite that angle measure pretty easily by the use of your diagram. That's what's going to determine whether the law of sines is going to be applicable. If you cannot use the law of sines, then it may be that the law of cosines is what you're going to have to do. The proof for the law of cosines I give to you here in the typed lecture notes. If you'd like to go through the proof, it starts out pretty similar to the law of sines, which is that you take an arbitrary triangle where the angles are not necessarily 90 degrees. There could be an obtuse angle in there, and either 2 or 3 acute angles, and we may not know. And we start by dropping a line perpendicular to the base, just like we did with the proof of the law of sines. Okay? In the proof for the law of sines, we then took the sine of an angle, like we took the sine of A and we took the sine of B, because it was after all, it was the law of sines. What are we going to do to prove the law of cosines? We're going to take the cosine of the angle instead. So let's take the cosine of A, and let's take a look at how these formulas work out here. Okay. First, when we drop that line perpendicular, we create 2 right triangles. Okay. Then notice, okay, by the Pythagorean theorem used on this left right triangle here, it would be true that x squared plus h squared is equal to b squared. Okay. And also within that triangle on the left, the cosine of A, which is equal to the adjacent over the hypotenuse, the cosine of A then would equal x over b. Solve that for x, we get x is equal to b times the cosine of A. Okay, this is starting to set up the proof that we're going to do. Now from the triangle that is on the right. On the right-hand triangle, the Pythagorean theorem would tell us that c minus x quantity squared plus h squared is equal to a squared. Okay? Where did the x and the c minus x come from? Well, we originally had a side length here that was side length c, because it's opposite of angle c that was up here at the top. And we simply split it up into two lengths, but those two lengths were not necessarily equal to each other. So we weren't just saying that each length was half of c. We didn't know the length of the two. What we knew about the two lengths, the length here AD and the length DB, what we know is that those two lengths have to add up to equal c. So if we call one of them a variable x, so just because we don't know what its length is at all, so we just give it a name and we call it x, well then the other one must be c minus x. Because then notice if we add the two lengths together, x plus c minus x, those will always add up to equal c, regardless of what x happened to be. Alright, so the Pythagorean theorem on the right-hand triangle gives us this formula here. Then if we expand that formula by foiling c minus x times c minus x, that gives us c squared minus 2cx plus x squared. Then we add the h squared equals to a squared. Then from the earlier triangle, the left triangle that we already looked at, we can then make a substitution. The substitution we make is for what x is equal to. All right, that's the primary substitution. We want to remove x from this equation here. So that x right there gets replaced by b cosine a, and already there we see we see the emergence of that extra term in the law of cosines. The minus 2cb cosine a term is going to show up there. And then we could replace the x by b cosine a again here, the one that's getting squared, but in fact we can do a little better because we actually have an x squared plus h squared, which was equal to b squared from the left-hand triangle. So we just replace those two terms then with the b squared. And we're done. We have the law of cosines then. We have c squared, we have minus 2c, we've replaced x by b cosine a from the left triangle, and we replaced x squared plus h squared by b squared. And here is our law of cosines. Rearranging the terms a little bit, to put it in the order that we're normally used to seeing the law of cosines. That is, again, if we set it up kind of like the Pythagorean theorem, where a squared would equal b squared plus c squared, we then subtract 2 times the product of the two side lengths, okay, the product of the two side lengths that were not the isolated side length, is what I suggested, times the cosine of the angle that is opposite of the isolated side length. Okay, there's our law of cosines, and it is now proven. And the proof would be exactly the same if we had chosen to drop this perpendicular from any one of these other angles. Like if we had taken from angle A, from vertex A, if we had dropped a line that was perpendicular to side length A, then we could have related the cosine of, for instance, angle C, okay, to the other side lengths, and we would have done one of the other law of cosines formulas. So some observations that we can make. Again, the law of cosines is quite expensive computationally. If we don't have to use it, we should just avoid using it. We should really reserve law of cosines for when nothing else is going to work, and that would be in the cases of side, 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 and side angle side. That's when the only option we have available to us is law of cosines. Then, after we use the law of cosines a single time, we should be able to use something else. Okay? After we use the law of cosines once, we'll find some other component of the triangle. We'll probably then be able to use some other less expensive formula in order to complete the solving of the triangle, if that's what we're attempting to do. And let's take a look at some examples. Okay? Oh, and remember the strategy. It's always read the problem carefully, draw yourself a diagram, okay? Labeling the known information and using variables to represent the unknown measures that are important in the problem. Okay? Determine which case you have. In other words, take a look closely at what information you know and what you're trying to know, and establish how you can find it. Can you find the missing information by just adding together the angles and saying that they add up to 180 degrees? Then just do that. Do you have an angle measure that is opposite a known side length? Then the law of sines is available to you. Okay? And if you absolutely need to, you use the law of cosines. Okay, so here's an example. Solve the triangle where the side length A is 76.3 meters, side length C is 42.8 meters, and angle B is 16.3 degrees. We're going to start by drawing and labeling a triangle. Sorry for the typo there. Okay, so triangle ABC, labeling the angles, labeling the side lengths, and then inputting the numerical values that were given. So side length C is the 42.8, side length A is 76.3, angle B is 16.3 degrees. Now assess what case we have. If we start at one of these known measures, this side length, and then we start rotating from there, we find that the very next angle that we approach is a known measure as well. So we have a side and then an angle. And then after that, the very next side is known as well. So this is a side, angle, side. Okay. Could we use the law of sines on this triangle? In order to use the law of sines, we need to have an angle measure that is opposite a side length, both of which are already known. Well, we know angle B, but we do not know side length B, not yet. So we would need to solve for side length B if we hoped to use that opposite of angle B. We know side length C. We could use law of sines then if we knew angle C, but we do not know angle C. Similarly, we know side length A. We could use law of sines if we knew angle A, but we do not yet know angle A. Furthermore, since we only really know one angle measure so far in this triangle, we can't use any basic formula to find the other angle measures. We can't use the fact that they add up to 180 degrees, for instance. Right? We won't be able to easily find angle A and angle C. We're going to have to, therefore, use law of cosines. We have just determined that the law of sines will not apply in this case. Right? And the sum of the angles being 180 degrees also will not apply. So we need to use the law of cosines at least to find one more component. As soon as we have just one more component, we can then reassess the triangle. For instance, if the law of sines will solve for us side length B, then we run the law of cosines to find side length B. Then notice, once we know side length B, suddenly we know a side length that is opposite a known angle. And that means we then have access to the law of sines. So then we can proceed with the law of sines to find then either angle A or angle C, whichever one we choose to go for next. After we then find another angle, then we would have two angle measures known, so then we can just use the fact that the sum of the angles is 180 degrees in order to find the third angle. So that's the approach we're going to take. The law of cosines can be set up then so that we can solve for the missing side length. Recall that the law of cosines, regardless of which of the formulas you use for law of cosines, will always incorporate 3 side lengths and 1 angle. And notice that we are already given here, we have 2 of the side lengths and we have an angle. So the law of cosines will allow us to solve for the one remaining side, therefore. Right? We already have an angle, we have 2 sides, so the law of cosines will allow us to solve for the remaining side. So let's use the law of cosines formula that is set up to isolate that remaining side, the one we want to solve for. And that's how we know to set up this law of cosines formula, starting with what looks like a Pythagorean theorem, where b squared is isolated. So the Pythagorean theorem isolating b squared would be b squared equals a squared plus c squared. Then we subtract 2 times the sides that are not the side length we've isolated, so 2 times a times c, times the cosine of the angle that is opposite the isolated side. That's how we know to set up the formula in this way. Then we start plugging in the known quantities. We can plug in what we know A is equal to, that's 76.3. What is C equal to? That's 42.8. Again, plugging in 76.3 and 42.8 again, right into the formula. And finally, angle B, which is the angle that we know, 16.3 degrees. All of this information then can go plugged into the calculator. Make sure you're set in degree mode on the calculator because we were given an angle measure that is in degrees. And then we'll be able to find first what B squared is equal to, and then we can take the square root, and that'll give us an approximation for B. We were told to round to 1 decimal place here. Okay, so we'll round B to 1 decimal place. We'll get 37.2 meters. Now we have side length B figured out. And again, once we have side length B, since we already had angle measure B, we now have a side length that is opposite an angle, both of which are known. That gives us access then to the law of sines. Okay? So I just want to suggest that here. In other words, if we wanted to solve now for angle A, for instance, or for angle C, we could use the law of cosines again. Consider that we now know 3 side lengths. We can plug in the 3 side lengths into a law of cosines in order to, for instance, solve for angle A or for angle C. But that's going to require us to do more computations. It's going to be more work to solve for either angle A or angle C than it would be to just use the law of sines at this point. So my preference would be to go to the law of sines. Okay? So let's say, for example, if we wanted to solve for angle C, we could set up the law of sines where we would input angle B and side length B because those are the opposite ones that we know. So the sine of angle B divided by side length B. And then that would be equal to the sine of angle C divided by the side length C, which is 42.8. That gives us an equation for sine. A sine of C is equal to some number. Recall that in solving this equation, where the sine of C is equal to some number, okay, the sine is equal to a positive quantity. And recall that the sine is going to be positive in either quadrant 1 or quadrant 2. Both of those quadrants would have angle measures where the sine is positive. However, when we use the arc sine function on the calculator, when we take the arc sine of 0.3229, for instance, the calculator will only give us the quadrant 1 solution. That does not mean that the quadrant 1 solution has to be the correct one. It just means that the calculator only knows how to give us quadrant 1. It doesn't know how to give us quadrant 2. It's up to us to establish that quadrant 2 was a possibility as well that we really do need to consider here. So the calculator gives us the 18.8 degrees. We have to determine that because sine is also positive in quadrant 2, that 161.2 degrees is a possible solution that we would really need to consider. Now, how do we know of these two angular measures which is the correct one for our given triangle? Well, one observation we can make is to recall that in any triangle, smaller angles are opposite smaller sides, and larger angles are opposite larger sides. For this particular example that we were given, the largest of the 3 side lengths was side length A. And that means that the largest of the 3 angles must be angle A. So only angle A can be the largest angle. Only angle A could be potentially obtuse. If any of these 3 angles are going to be more than 90 degrees, if they are, it would have to be angle A that is the one that is more than 90 degrees, because angle A is clearly going to be the largest of the 3 angles. For that reason, we choose the smaller angle, 18.8 degrees, for this example. Okay, so I really want to be clear about this. We do not always choose the answer that the calculator gives us. We have to consider, when we use those inverse trig functions, that there are other quadrants where we could have found solutions to our equation. And we really do need to consider whether in the particular example we're working on at the moment, which one of these solutions is really going to be the correct solution for this given triangle. All right, with the numbers being changed just a little bit in this exercise, okay, the answer could have been 161.2 degrees. Okay, so I really want to be clear about that point. Just because the answer here happened to be the quadrant 1 solution does not mean the answer will always be quadrant 1 solution. You really do need to consider the other solution as well, okay, and try to justify which of these two is really going to be the correct solution, right? And I gave you a way that you can justify it. Now, you could have set up the law of sines to solve for angle A. If we had set it up to solve for angle A, let's take a look at what that would have looked like, okay? Why I mention that is because, again, angle A is going to be the largest of the three sides. So let's set it up that way. Okay, so this is, right, from the, not from the worksheet, right, from the notes. Okay, sine of B over B is equal to the sine of A over A. We'll plug in angle B, which is 16.3 degrees, side length B, which was 37.2. Okay, and then angle A we're trying to solve for, and side length A is 76.3 meters. And then we can go ahead and solve this for sine of A. I'm going to move sine of A over to the left-hand side. That's okay. Multiplying both sides by 76.3, I get 76.3 over 37.2 times the sine of 16.3 degrees. Okay, so we'll go to the calculator and it'll come up with an approximation out to several decimal places for this quantity over here. Make sure we're set in degree mode on the calculator. 76.3 divided by 37.2, and then multiply that by the sine of 16.3, and I'm checking that I'm in degree mode on the calculator. Okay, and the answer I get is approximately 0.575668554, right? Several decimal places of accuracy. Okay, therefore one possible value for A, and again I'll note at this point, so the sine of A now is a positive number. Right, and sine is positive in both quadrant 1 and quadrant 2. Okay, that is that we could have angle A could be this measure, I'll call that A1, or it could be this measure, and that's A2. Clearly A2 is greater than 90 degrees. That would force us to have an obtuse triangle. Okay, we should see if that's actually what we have or not. Okay, but A1 would be found by taking the arc sine of this number, 0.57567, we'll call that. And that's approximated by, let's see, on the calculator, I get approximately 35, okay, 0.1 degrees. After the 1, then there's a 4.64643. So that's A1. Now A2 would be approximately 180 degrees minus 35.1 degrees. That would put us in quadrant 2. Okay, and that is what, 144.9 degrees. Okay, right, 144.9 degrees. So we need to consider which one of these two is going to be the correct value for the given triangle. Okay, now how do we know? Again, angle A has to be the largest of the three angles. Okay, well, the only angle we had so far, this is assuming that we didn't already know angle C. Okay, we only had angle B, so all we know right now is that angle A has to be more than 16.3 degrees. But both of these are more than 16.3 degrees. So how do we know which one it is? We might need to look further then. We might need to consider, well, what is going to be angle C in order to determine that? In other words, we don't automatically assume that angle A has to be the 144.9 degrees. We just know that it has to be more than the other angles that we have. Okay, so we need to consider that what would angle C be in either of these cases. So if A is equal to 35.1 degrees, then what would angle C have to be? Well, it would have to be 180 degrees minus the 35.1 degrees and also minus the 16.3 degrees, which was angle B. What would that give us? Well, that would give us, let's see, on the calculator, 128.6. 128.6 degrees. Is that the value of C? Could that be the value of C? Take a look at the triangle again. Could we say that angle C is more than 90 degrees? Again, we could not, because angle C, right, has to be the middle of the three angle measures. It can't be larger than angle A. Okay? So this is not a possible value of C. Okay? Why? Again, because angle A must be greater than angle C, since side length A is greater than side length C. Okay? So what does that mean about, is A equal to 35.1 degrees? No, it's not 35.1 degrees. Okay, so I hope you follow my reasoning here. Okay. Then that means that angle A must be the larger of the two possibilities. It must be 144.9 degrees. Okay, and if that was the case, then C would be 180 degrees minus 144.9 degrees minus 16.3 degrees. Okay, and let's see, what is that going to be? Minus 144.9 minus 16.3 is 18.8 degrees, and that's exactly what we found that angle C was when earlier we solved for angle C by using the law of sines. Okay. All right, so this over here, this work here is to demonstrate, again, the importance of considering that there's more than one solution to a trigonometric equation, and when you hit that inverse trig key on your calculator, you're only going to get one of those solutions, but you really do need to consider other possible solutions, and if possible, you want to exclude other possible solutions, okay, for reasons that are logical, that make sense. In this case, I was using the logic of smaller sides are opposite of smaller angles. Okay, so that would complete this triangle then. Okay, so we would have the three angle measures and the three side lengths as well at that point. Right? This jumped onto the next page. Angle A was 144.9 degrees. Okay. All right, so that again was a side angle side. Right, that was a side angle side case whereby we used the law of cosines to find the missing side, then we used the law of sines to find a missing angle, and then we were able to find the last angle by using the fact that the sum of the angles had to be 180 degrees. That was the side angle side case. Every other side angle side case you do will be similar in construction to what it is we did here. You'll do the law of cosines, then you can do law of sines, and then you can do the sum of the angles is 180 degrees. And so here I give you an example, side, side, side. That's all it takes, is I just give you one example of each case, because then in any other problem where you do the same case, all that changes are the numbers you're given. Okay? And like whether you're setting up the formula where the a squared is isolated or the b squared or the c squared, it's the same process in every case though. That's why I don't have to give you like 10 examples for law of cosines. I just give you one of each case. And the idea is you should now be able to do it anytime you have that case by drawing yourself a good diagram and labeling it, right, and following the strategy that I've outlined for you. Okay. So here's a side, side, side case. Solve the triangle where A is 0.48 yards, B is 0.63 yards, C is 0.75 yards. Start, as always, by drawing and labeling the triangle. So we label the three vertices and the three side lanes, and then we put in the numerical values. So now we have to determine at least one of these angle measures. So just pick one of the angles. It doesn't matter which one, any one of them that you want. Okay, and so down here, for instance, I'll solve for angle A. If you want to go through and set up a law of cosines right now for, let's say, angle C, you could do that. It would be rewriting the formula as C squared equals A squared plus B squared minus 2AB cosine C. So you can rewrite the formula whereby you're trying to solve for the angle C instead. Right? So you would be isolating C squared over here, all the A's and B's would be here, and angle C would be here. Okay? And it would work. Okay? You should be able to get that to work. So you plug all the numbers in that were given for the side lengths. The angle, in this case angle A, is the one variable we're solving for right now. Okay? And then you go to the calculator and you try to calculate all this. All right? Remember if you're going to be rounding in the midst of this, if you're going to start rounding numbers before the end of the problem, you should take more decimal places than you might think are necessary. Maybe take all the decimal places off of the calculator for accuracy. If you were, for instance, to look at I've said this before, it bears repeating maybe for accuracy. It says round to one decimal place. That means your final answer should be rounded to one decimal place. If you were to start rounding to one decimal place here, for instance, if you were to square 0.48 and round that to one decimal place, and then square 0.63 and round that to one decimal place, etc., there's a good chance that you're not going to get the correct answer that's most accurate in the end, because you'll be dealing with some kind of accuracy error. Okay, I've mentioned that before. So save the rounding until the very end of the entire process in order to get the most accurate results. Okay. All right, but this is going to boil down to a cosine equation. The cosine of A is equal to some number. Now, what quadrants would have solutions to this equation? Well, we have the cosine is equal to a positive quantity, and the cosine is going to be positive, recall, in quadrant 1 and quadrant 4, in those two quadrants. Okay? That is, whenever you solve this equation, you would get solutions that are either from 0 to 90 degrees or between negative 90 degrees and 0 degrees, for example, or between, let's say, 270 degrees and 360 degrees. But notice, right, logically, you cannot construct a triangle that has either a negative degree angle in it. Okay? That would not occur. And you also would not be able to build a triangle that has an angle that is between 270 and 360 degrees. No such triangle exists. Okay? So, when we solve this equation by using the arc cosine, we don't have the complications we had when we used the arc sine. Okay, the solution we get from the calculator for this equation, fortunately, is the only really reasonable solution that we would have for that angle. Okay, so we took the arc cosine of 0.774, we get a quadrant 1 solution, 39.5 degrees. We do not need to consider a quadrant 2 solution. All right, this is reiterating what I was just saying, but saying it in a different way. We do not need to consider 180 degrees minus this. Why? Because cosine of a quadrant 2 angle would not be positive. All right? This equation right here, all right, doesn't have a quadrant 2 solution because cosine is not positive in quadrant 2. For that reason, we don't need to consider a quadrant 2 counterpart to this 39.5 degrees. Right? That is really true because we're using a cosine equation here. Right? But when we were using the sine equation earlier with the law of sines, that's where we needed to consider quadrant 2. All right, so we have our angle A. We have 39.5 degrees. Now that angle A is determined, notice we now have an angle opposite a side. That gives us access to the law of sines. So we can set up the law of sines to solve for either angle B or angle C. And again, as in the previous example, that is going to give us a sine equation. The sine of B is equal to a positive number. That's where we have to consider where our solutions could now be. For B, that is, for angle B, the solutions could be in either quadrant 1 or quadrant 2. So we have to consider both the quadrant 1 and quadrant 2 solutions, just as we did in the previous example. Consider what the smallest angle would be, what the largest angle would be in the triangle as well. Okay, by virtue of what side it is opposite of. And that's how we can determine what is the correct angle. Okay, once we have angle B figured out, we can figure out angle C. You could have set up the law of sines to solve for angle C. Okay, go for it that way. Okay, angle C in this case will turn out to be 83.9 degrees, and that's the measure that's going to work. All right, so you can now solve triangles in the cases where you will be required to use the law of cosines as the first step. If you are going to use the law of cosines for either of those cases, notice that right after you use the law of cosines once, you then can move into the law of sines. And then after the law of sines, you can then use the fact that the sum of the angles in the triangle will be 180 degrees in order to find the remaining angle. Okay. So now what I want to do is I want to take a look at a couple of applications, so word problems, okay, which happen to lead us to situations that we can use the law of cosines for. The first one's here. The diagonals of a parallelogram are 56 inches and 34 inches, and they intersect at an angle of 130 degrees. Find the length of the shorter side. First, what is a parallelogram? Okay. A quick, Google search could tell us what a parallelogram is if we forgot, or, you look in their textbook as well, okay, or any geometry book. So parallelogram is a four-sided figure which has two sets of parallel sides. So here's, in general, a parallelogram. So, for instance, let me label some of these sides. I'll call this side A, this can be side B, this can be side C, and this can be side D. So what makes it a parallelogram is that side A is parallel to side B, so that symbol means parallel to. And C is parallel to D. Okay, parallel, parallel. So they travel in the same direction. This is a parallelogram. A rectangle is a special case of a parallelogram, and so is a square, because a rectangle and a square would also have two sets of parallel sides. Okay, but in general, here's a parallelogram. It says the diagonals of the parallelogram. Well, what are the diagonals? The diagonals would be from one corner to the opposite corner. That would be a diagonal of this parallelogram, and then here's the other diagonal. So these are the two diagonals. So let's say I call this, this is diagonal 1, this is diagonal 2. Okay, here's our two diagonals. Okay, it says the diagonals are 56 inches and 34 inches, and they intersect at an angle of 130 degrees. Find the length of the shorter side, meaning the shorter side of the parallelogram. So one of these diagonals is 56 inches and the other is 34 inches. By observation, which one looks like the longer one? The one that goes from here to here, that looks like the longer one. Therefore, this length is 56 inches. Okay? And it would be correct. Okay, we can show geometrically that this is correct. That this triangle and this triangle are congruent. They're the same size, and these two triangles are also the same size. All right, they have to have, for instance, this angle right here has to be equal to this angle right here, and this angle right here has to be equal to this angle right here, for example. Okay, and the side lengths. This side length and this side length, these two sides have to equal each other. This whole length is 56 inches. Then it would be true that this length here is 28 inches from here to here. And also from here to here, that is 28 inches as well. And the shorter diagonal is 34 inches. So the distance from here to here is going to be 17 inches. And the distance from here to here is also 17 inches. So they say that the diagonals intersect at 130 degrees. Well, notice that these two angles right here have to add up to 180 degrees. They must be supplementary angles. But only one of them can be more than 90 degrees, and clearly that is this one right here. So this is the larger angle right here. So now I'm going to extract from this a triangle. I'm going to take this upper triangle right here, the one where I circled that angle right there. Okay, because that has relevant information in it, that triangle. Okay, this angle right here, right? So this is the side length C right here. This angle right here is the 130 degree angle. Okay, this side length right here is 28 inches. And this side length right here is 17 inches. My triangle kind of looks isosceles. This is not to scale, right? These two side lengths are not equal to each other. I know it kind of looks like it in my diagram. Okay, I could have done a better job drawing that this one is a longer side than that one is. But I've labeled it, okay? So we have a side and an angle and a side. So we have a side angle side case. And we want to find a missing side, C. All right, and so therefore, we can relate these quantities of 3 side lengths and an angle through the law of cosines. The law of cosines we can set up to solve for our missing side length C by isolating a C squared. So C squared would equal A squared plus B squared, that looks like Pythagorean theorem, then incorporating law of cosines, minus 2 times these same 2 side lengths, that is the side lengths that are not the one that's isolated. So minus 2A times B times the cosine of the angle that is opposite the side length we want to solve for. So angle C. So I write out the complete formula with all the variables in it before I start plugging the numbers in. Okay, make sure the formula is correct. So C, the side length C, we don't know, but A, B, and angle C we do know. So for instance, okay, it doesn't matter which one we want to call side length A and side length B in this case. In fact, I should go back to my original triangle now. I maybe should have chosen different letters maybe for those 2 sides right there. Okay, because now I'm going to be using lowercase a and lowercase b to represent these side lengths instead. Okay, so A is equal to 17, so we have 17 squared. B is 28, so we have 28 squared. Minus 2 times 17 times 28 times the cosine of 130 degrees. So now we can go to the calculator and plug all this into the calculator and get an approximation for C squared. So I have 17 squared plus 28 squared minus 2 times 17 times 28 times the cosine of 130, and I make sure I'm in degree mode, and I get approximately 1680, well, 4.933, so I'm getting approximately 1685. Okay, I can see that there are, looks like 2 significant digits on the side lengths up here, so I'm going to look for C to be 2 significant digits as well. So C is approximately the square root of 1685, and let's see, the square root of 1685 is approximately 41. It's 41.049. So to 2 significant digits, that's approximately 41. Okay, what were the units of measurement in this exercise? It was inches. So the longer side length is 41 inches. I just found the longer side length, and I just realized we were asked to find the shorter side length, weren't we? Alright, so I'll just consider that to be some little bonus work I did. Alright, now let's go ahead and find the shorter side length then. Okay. Alright, so I'm going to call this shorter side length, I guess I'll call it X at this point. Alright, so I'm going to extract one of the other triangles. So I'll take this right-hand triangle, for example. So if that angle there was 130 degrees, then this angle here, which must be a supplement to it since they lie on a straight line, this angle would have to be then 50 degrees. So let's extract that triangle then. And then side length X. And so this is a 50 degree angle right here. Okay, we have 28 inches here and 17 inches here. Okay. So x is now the shorter side. Let's set up the law of cosines then, because it's an opportunity to set up the law of cosines for, let's say, the variable x. Then, okay, so this would look like x squared is equal to, all right, what I said, this was a, this was b, for instance. How about x squared is equal to a squared plus b squared minus 2ab times the cosine of angle x? Okay, so I'm using an uppercase x there for the angle. All right, so x squared is equal to 17 squared plus 28 squared minus 2 times 17 times 28 times the cosine of 50 degrees. Okay. All right, back to the calculator. All right, 17 squared plus 28 squared minus 2 times 17 times 28 times the cosine of 50, making sure you're in degrees. And I'm getting approximately 461. Take the square root then. X is approximately square root of 461. And I'm getting 21.47. Okay, so that's approximately 21 inches. And so that would be the length of the shorter side. All right, so now we have the longer side and we have the shorter side, and that's fine. Okay, let's take a look at one more example here, application problem. The distance between two ships. So two ships leave a harbor entrance at the same time. The first ship is traveling at a constant 18 miles per hour, while the second is traveling at a constant 22 miles per hour. If the angle between their courses is 123 degrees, how far apart are they after 30 minutes? Let's start with a diagram. So there's a harbor. Okay, and from the harbor, these two ships leave. So we have a ship that is maybe traveling in this direction. I'm using a vector here to note what direction it traveled, in fact. Okay, just that arrow is all I'm saying. And then we have another ship that is, going, let's say, this direction. Because we're told that the angle between their courses is 123 degrees. Now we're told that one of the ships is going 18 miles per hour, the other is going 22 miles per hour. Okay, we might recall that uniform motion, distance is equal to rate times time. Okay, where rate is a speed. Okay, so for instance, the amount of miles that a ship has traveled is equal to the miles per hour, all right, times the number of hours. Right? Because then hours would cancel hours, and so miles would equal miles. So the rate is given in miles per hour, for example, or it could be meters per second, or feet per minute, or things like that. And then time is a unit of time. Make sure the units of time match up so that they cancel out appropriately. And in this case, we're told, okay, so one of these ships goes 18 miles per hour, so D is equal to 18, okay? And times the amount of time, but the time is 30 minutes. 30 minutes. Well, 30 minutes is equal to half of an hour, right? So if I were to put 30 in here, that would be 30 minutes. I would need to multiply then. We would need to multiply by 1 hour over 60 minutes to do a unit conversion there, because the 18 is in miles per hour, and we need to be able to cancel hours with hours. In other words, we get 18 times 1/2. So the distance for ship 1, so we'll call that D1, okay, 18 times 1/2 is equal to 9. And that distance would be measured in units of miles. Okay, that was the slower of the two ships, so I'm going to make that the smaller of these two sides. Okay, so this distance here is 9 miles. Okay. The distance up here, okay, so this is D1 down here. The distance up here, D2, is found by taking the 22 miles per hour and multiplying that by a half of an hour. That means that the other ship went 11 miles. Okay. We're asked After that 30 minutes of time has passed, then how far apart are the ships? Okay, because they left at the same time, they traveled on these courses. This distance here is then what we're trying to solve. All right, to solve for. So I'll call this side length C. Okay, and I'll also go ahead and let's simplify our triangle a bit here. Okay, let's clean it up a little bit. Okay. We want side length C. We have the 123 degrees here. Okay, let's say I call this A. A is equal to 11, and this B. B is equal to 9. Law of cosines then. Why law of cosines? Because we have a side angle side case. We want to solve for a side when we already have two sides and an angle, so the law of cosines will work for us. If we could have used a law of sines, then we should use the law of sines. But we can't use the law of sines because, again, we don't have an angle that is already known opposite one of the side lengths that we already know. Okay, so we're going to use the law of cosines, therefore. So C squared is equal to A squared plus B squared minus 2AB times the cosine of angle C. Therefore, C squared in this case is equal to 11 squared plus 9 squared minus 2 times 11 times 9 times the cosine of 123 degrees. So let's go to the calculator and find our approximation for C squared. Okay, 11 squared plus 9 squared minus 2 times 11 times 9 times the cosine of 123 degrees. And I'm getting, this is approximately 309.8. Okay, and then C would be approximated by the square root of 310 or 309.8. We're going to want to go to two significant digits here for the distance measurement. So let's take the square root of our answer. And let's see, I'm getting about 17.6. Okay, 17.6. So if I want two significant digits, then I'm going to say C is approximately then 18 miles. So the two ships are approximately 18 miles apart. Now that seems reasonable considering that the angle C is obtuse, so the side length C is going to be the longest of the three sides. And the value of C that we got is certainly larger than 9 or 11. And also, it seems a reasonable measure. It's not unreasonable. They went 9 miles and 11 miles, and I wouldn't expect C to be really large, like hundreds of miles or something like that. Right? So it seems reasonable. For instance, if we put in the answer like 310 miles, that would not seem reasonable to me. I wouldn't expect that if one ship went 9 miles and the other went 11 miles, I wouldn't expect to find a distance of like 310 miles between them. That's just using, a reasonable, logical sense here to check the validity of an answer. So 18 miles seems like a reasonable measure to me. Okay, so that finds the distance between them after that 30 minutes has passed by using the law of cosines. Okay, so check out the homework then on your law of cosines. And in general, when solving a triangle, know that you want to draw a good diagram, label the known information, label the unknown information, and try to determine what is your best approach for solving that triangle. Right? Should you use law of cosines? Should you use law of sines? Take a look at the clues to indicate which formula is going to be, which formulas are available to you, and always choose the formula that's going to be less work. You might as well. All right. And anytime that you're using the inverse trig keys on the calculator, again, it's important to consider the quadrants like we talked about when solving trigonometric equations. The calculator is only ever going to give you one answer, but that doesn't mean that has to be the correct answer. You really want to consider the underlying geometry in the exercise, like what is the longest side length in the triangle versus the largest angle in the triangle. And use your diagram as well, okay, in order to determine whether the answers the calculator is giving you are in fact the correct answers, even when you've done all the math correctly to that point. Okay, So let me know if you have any questions. You can send me an email, and remember to talk to the tutors as well if you have any questions or need extra help from them as well. All right. Okay, so take care.